Good morning, students.
Good morning, ma'am.
Good morning. Today we will learn clauses in FOL, first order logic.
Okay, ma'am.
Yesterday we discussed about this is collimization, pre-next
Right.
norm. All right. So what is a clause? A clause is defined as a closed formula. It is a formula and it is in this form. The form is L1 union or L2 union L and so on up to LM, where each L is a literal and all variables occurring in L1 up to Lm are universally quantified. Universally quantified means we discussed in detail yesterday. We have quantifiers for all and there exist. Universally quantified means for all. The scope of variable appearing in the clause is the clause itself. This is the clause. The scope of these variables is within this clause. All right. Uh, Next one. Let S be a set of clauses C1, C2, and Cm, which represents a standard form of a given formula alpha. Then there are these following definitions will hold. What are these definitions? A formula alpha, al alpha is a formula, is said to be unsatisfiable if and only if corresponding set S is unsatisfiable. Essentially, there is a set S comprising of clauses C1, C2, and up to Cm. This set represents a standard form of a formula alpha, and this formula alpha has got a few properties. The first property is it is said to be unsatisfiable if the set S is unsatisfiable. S is said to be unsatisfiable if and only if there exists no interpretation that satisfies all the clauses of S simultaneously. Yeah, in first property, we talk about a formula alpha to be unsatisfiable when S is unsatisfiable. The question that comes up is when do you call the set S uh, unsatisfiable? Set S is said to be unsatisfiable if and only if there exists no interpretation. We learned that we have got some domains and variables, and based on the value of domain and variable, we can interpret whether the formula is true or false. Apparently, here, if there is no interpretation that exists for all the clauses of S, then S is said to be unsatisfiable. Again, there is a question when set S is said to be satisfiable. Well, when there exists an interpretation that satisfies all the clauses of S simultaneously. When there are all the clauses of set S um, can be interpreted, S is said to be satisfiable. The last property is that alternatively an interpretation I is said to model S if and only if I models each clause of S. S is a set of clauses. C1, C2, and Cm. There is some interpretation for all the clauses. When an interpretation I is set to model S, if and only if I models each clause of S. If interpretation I models each clause of S, it is said to be um, modeling the set S. All right. So these are the clauses in FOL. Clause is a closed formula written in this format: L1 union L2 union L3 and so on up to union LM, and where each L is a literal. Every variable in this uh, literals are universally quantified. Furthermore, we studied there is a set S comprising of the clauses C1, C2, and Cm, and S represents a standard form of formula alpha, where alpha is said to be satisfiable when S is satisfiable. Alpha is said to be unsatisfiable if S is unsatisfiable. S is said to be unsatisfiable when there is no interpretation of for all the clauses in S. S is said to be satisfiable uh, when there exists an interpretation that satisfies all the clauses of S. An interpretation is said to model S when it models um, each of the clause of S. That is about clauses in FOL, that is first order logic. Next one is resolution refutation method in FOL, first order logic. A resolution refutation method in first order logic is used to test unsatisfiability of a set of clauses. Unsatisfiability. All right. It tests whether the set is unsatisfiable, corresponding to the predicate formula. There is a predicate formula. If S is said to be unsatisfiable, it can be tested by uh, this one, resolution refutation method. And it is an extension to the resolution refutation method described earlier for propositional logic. When we studied propositional logic, we learned resolution refutation method. This first order logic specifies an extension to the resolution refutation method of propositional calculus. A deduction of a contradiction from a set S of clause is called resolution refutation of S. We have been deducing or deriving the formulas when we are deduction of a contradiction. When you are deducing through contradiction, the set S, it is called as resolution refutation of S. And what does resolution principle checks? It basically checks whether the contradiction is contained in or derived from S. Resolution for the clauses containing no variable is simple and similar to that used in propositional logic. If there are clauses that contains no variable, it is same to the principle of resolution in propositional logic. However, it becomes complicated when clauses contain variables. In such cases, before resolution, two complementary literals are resolved after proper substitution, so that both have literals that have arguments. When the clause contained variable, before resolution, two complementary literals are resolved after proper substitutions, so that literals can have arguments. Let us look at an example to understand it better. Find the resolvent of two clauses CL1, CL2, where P, Q, and R are predictive symbols. X is a variable, F is a unary function. CL1, this is first clause. CL2 is the second clause. CL1 is equal to P of X union Q of X. X is a variable and P, Q, R are predicate symbols. P, Q are predicates. X is a variable. F is a function in clause 2. P and R are predicates. X is a variable. There is, in this example, a resolvent has to be found for these two clauses. If we substitute f of a for x, instead of just x, we are substituting f of a in CL1 and a for x in CL2. In CL2, in place of x, put a. In CL1, in place of x, put f of a. Apparently, this turns out to be CL3 P of f of a union Q of f of a, CL4 not P f of a union R of a. Look, what happens is P of x, in place of x, we are putting f of a. Union Q of x, in place of x, we are putting f of a. For CL2, not P, in place of x, substitute a value a. So it makes it not P of f of a union R of x. In place of x, put a. This makes CL3 and CL4 to have complementary literals. What are complementary literals? P of f of a, not P of f of a. These two are complementary literals. And the resolvent is generated by taking a disjunction of literals from parent clause after eliminating pair of complementary literals. When we eliminate this P of f of a and not P of f of a, Whatever is left, that both the literals are taken and joined by disjunction, which is union or which is or. Uh, and then we notice that there are no variables. There was a variable x, and later x was replaced by a. A is a constant. A is not a variable. X is a variable. Therefore, here Cl3 and Cl4 do not have variables. These are called ground instances of Cl1 and Cl2. If f of x is substituted for x in Cl1, another clause would have been obtained. P of f of x union Q of f of x. Then Cl dash is equals to resolvent of Cl1 complement and Cl2, which are Q of f of x. This is left over, no? Q of f of a. Here, you are bringing x back. R of a instead of R of a, write R of x. Finally, this is the resolvent. Cl is an instance of Cl dash, and Cl can be obtained from Cl dash by substituting A for x. If you put A for x, you obtain Cl. Assuming that the set of clauses is given by S of C1, C2, Cm, and L is some predicate formula, we can state some important results as given below. What are the results? These are the results. 1, 2, 3. The first says that, the first one, L is a logical consequence of S. If and only if S union not L is equal to C1, C2 up to Cn or Cm here, up to Cm, not L is unsatisfiable. L is a logical consequence of S if and only if because we have to deduce by contradiction. Therefore, here you are taking not L, and this is unsatisfiable. We can say that goal L is deduced from S. Not L may give rise to more than one clause. The example is L is equals to P of x union Q of x and R of x. For this example, not L could be written as not P of x union Q of x and R of x. Individually, you can use not P of x and not Q of x and R of x. This is in the parenthesis. When it is in parenthesis, we can replace or with and specify not for P and Q. But for R, to specify it for R, Here you have to change this and to or. Later R would be negated. So here not P of X, this or would become and, not Q of X, this and becomes or, and not R of X. What is this one? This one is expanding this formula to incorporate not symbol for each individual um, 1 minute. Now not L is converted into two clauses. What are the two clauses not L is converted into? This not P of X, comma. This is taken into parenthesis. Means now you can using or you can open it and you can put wherever there is and, in place of and you can put a comma. It's like the two separate clauses. And specify two separate clauses. Or means it is one clause. You cannot say or comma in place of or. This is first one. The second one states that soundness and completeness of resolution theorem states that there is a resolution refutation of S if and only if S is unsatisfiable. And a deduction of a contradiction from the set S of clauses is called resolution refutation of S. Soundness and completeness of resolution theorem. You know, we learned a resolution theorem that is said to be sound and complete when there is a resolution refutation of S. S is the set if that set is unsatisfiable. And whatever has been deduced through contradiction from the set S of clauses is called resolution refutation of S. And L is finally the third point is L is said to be logical consequence of S if and only if there is a resolution refutation of S union not L. You know, logical consequence means what? S is one set. It has got clauses. If you are appending L also to S in negation form, this would be this is possible only if there is a resolution refutation of S union not L. What is logical consequence procedure? First, a set S is obtained that includes all the clauses by converting alpha k. Alpha is a formula to its standard form. And clauses can be obtained from standard form, as we discussed scholemization or standard form through that. And there is a need to show set S union not L. It is unsatisfiable by deducing a contradiction using the resolution method. It's all about contradiction, deducing. If the contradiction is obtained, then conclude that L is a logical consequence. If there is any contradiction exists for set S, then the formula alpha 1, alpha 2, up to alpha n. When L can be deduced through contradiction, it is said to be a logical consequence of S. If there is no such uh, contradiction deduction exists, then L is said to be not a logical consequence of S. Further, choice of clauses to be resolved. There are some steps in order to choose the uh, clause to be resolved reasonably. If the clause that need to be resolved at each step is made in a systematic way, the resolution algorithm will surely find a contradiction. If it is done in a systematic manner, it can find. And there are various heuristics for making the right choices that can speed up the process considerably. And the steps are, first one is, after the first step, choose a clause from the negated goal clauses as one of the parents to be resolving this because the contradiction. And if that exists, it implies that the goal that we are trying to prove occurs. Using the resolvent for further resolution with an existing clause, both the clause should contain one pair of complementary literals. If there are no pair of complementary literals, they cannot be cancelled or they cannot be removed. And further, like this. All right. If such clause do not exist, then resolve any pair of clauses that may contain complementary literals. And resolve using clauses with a single literal whenever possible. Such resolutions generate new clauses. Eliminate tautologies as soon as they are generated. These are the steps. And to prove the above statement, we need to convert alpha into a set of clauses with the help of equivalence laws. We know there are some equivalence laws. P of x and not Q of x implies Q of P of x. This can be written as P of x and not Q of x union P of x. If you have to convert, this implies it would be not or. That's why you got not or. Further, p of x and not q of x and not of p of x. This is spread across this parenthesis. When you expand this, it gets to just a q of x, because not gets cancelled. P of x and q of x. Not this not goes away. Then q of x and not p of x. This will be remained. Why this will be remained? Because it is p of x. After you use this not over this expression, it gains. It gets this not for that variable. All right. The set of clauses written as S is equals to P of x, comma Q of x, comma and P of x. And there is a contradiction in S itself, because P of x and not P of x. S is unsatisfiable, and consequently alpha is unsatisfiable. When do you call S unsatisfiable? When the contradiction exists. What is the contradiction? P of x and not P of x. Here also you can see P of x and not P of x contradiction arose. Because of that, S is said to be unsatisfied. Another problem is show that Q of A is a logical consequence of formula alpha and beta, where alpha is equals to for all x, parenthesis, P of x implies Q of x, and beta is equals to P of x. How do you prove this? You write in this manner. This P of x in place of x for this is for all x. All right, we have to add not of q of x, q of negation. What is the goal? Goal is this q of x. Negation of goal has to be added. Here we can see not of q of a, not p of x or q of x, p of a. Then what happens here? These are complementary, not q of a, q of. So actually, we are taking a in place of x. So here we are left over with not p of a. And then from this and this, we obtain p cancel, we obtain x, just the x. All right, with this we have done with the predicate calculus and first order logic. This logic programming we will study in tomorrow's class. Tomorrow is a holiday, in day after tomorrow's class. All right.